All right, so first things first, Christmas was like 3 weeks ago, so I think we should probably go ahead and get rid of the tree. Okay, there we go. I think that looks better. All right, so today we're gonna make something really cool, okay? We are going to make a CPU usage visualizer in Bash. Now, what I mean by that is, you ever used a program like, htop or btop or something like that, they sort of give you a nice little visualization. You can see like a bar that shows how much CPU you're utilizing at the given moment. So here, I'll put an example up here, but if you have like a CPU, let's say you have like 4 cores or 8 cores, you can see how much each core is being utilized at that given moment. So that's pretty cool. It's nice to be able to see it like that. I want to show how you can get that information yourself. We're going to write something like that from scratch. We're going to use Bash, and we're going to use nothing but Bash built-ins to actually do this. So yeah, let's jump into the code and I'll show you exactly what we're going to be working on here. All right, so the first thing you probably notice here is this is not my normal prompt. We are logged into a Linux machine. So we're not on my Mac, we're not on a Lumos machine, we are running on Linux. This is going to be specifically for Linux. The reason I'm choosing Linux here is because Linux has a very interesting proc file system. So if you've ever seen it before, /proc, you can see there's a whole bunch of stuff going on here. We have a directory for each PID. This is each process that's running on the machine. And then we have a whole bunch of other stuff here. It's sort of a dumping ground of just cool and useful information. So some of it's formatted in binary data, some of it's like string data. Very interesting, very unique, but because of this, we're going to take advantage of this. Some of the data here is in a string format, so we can parse this directly in Bash without any sort of weirdness, which is pretty cool. The other thing you may notice is that my voice sounds a little bit hoarse right now. I don't know what's going on. I'm kind of getting over like a little bit of a cold, so I apologize. The voice is going to be very, very low, but hopefully it gives you that nice kind of, ASMR vibe as we go through and code this. I'm also gonna have to edit out a bunch of coughing, but I'll edit it out so you won't even know it's there. So of course, I want to stress this point. This is really only going to work on Linux or anything that has a sort of Linux compatible proc file system. I know FreeBSD has like linproc, I think. Illumos might have lxproc. It's sort of a Linux compatible proc file system. We're not going to worry about those. We're just going to program this directly for Linux. Because for example, if I were on my Mac, let me go and log out here. I don't have a proc file system. Mac does not have a proc file system. FreeBSD, I think you used to have one in the past, but it's been deprecated, so now you don't have it. You won't have a /proc file system. Illumos is a little bit different. You will have a proc file system, but it's different. As you can see, we only have the PIDs there. There's not other things like devices, crypto, CPU info, things like that. This is a way different type of thing here. So if I want to get information about, let's say, myself, I can get something like PS info, and you can see that it's binary data. So in order to parse this, you would need the headers that ship with your kernel. A lot of this stuff is very stable. These interfaces are pretty stable. They haven't changed in a long time, but we're not going to be looking at these operating systems. We are going to be specifically on Linux. Let's go ahead and go back into the Linux machine. We're going to be on Linux. We're going to have the proc file system here, and a lot of the data is just going to be strings. So we can parse it directly in Bash and just sort of use all the built-in facilities that Bash has to offer. So yeah, I don't have a good name for the software. We're just going to call it Viz for now for visualizing. And the first thing we want to visualize is CPU usage. So remember I mentioned a couple other programs out there. If you have like htop, you can see at the top, we have our CPU usage here. We have 4 cores in this machine. This is a virtual machine. And you can see that of the 4 cores, we're like 0.0, 0.7%. So it'd be nice to have something like this, a sort of bar graph that shows it to you like this. If you were in, btop, people have told me to check it out. You get kind of the same thing. As you can see here, we have the CPU, like the global usage of CPU, and then we have C0, C1, C2, and C3. Those are the 4 different CPUs I have. So pretty cool output. We're going to create something not as fancy as that, but we're going to create something visual that you will be able to follow along with and create, in a small video like this. Let's go ahead and make a new script here. We'll call it CPU. We don't need a fancy name. Bin env bash. That lets us know that we're writing a bash script. Let's go ahead and save it. Okay, let's make it executable. This is just an empty script, so if we run it, we get nothing. Hey, that makes sense. So we have a script ready to go. Well, what's the first thing we need to do? We need to be able to get the CPU statistics out of the proc file system. So to do this, there's a couple different ways. There's also the sys file system. What I'm saying is SYS. So we could use the sys file system, but instead I'm going to opt for proc stat. So this is a file that exists. It's in the proc file system. Let's go ahead and look at this proc stat. And you can see there's a bunch of stuff here, but it's strings. It's ASCII data. This is beautiful. There's no binary data. We don't have to do any sort of weird parsing. We can just parse this like it's a string. In fact, let's look at the top line here. We have CPU, and then we have a whole bunch of numbers. Then we have CPU 0, CPU 1, CPU 2, and CPU 3. I have 4 cores, so that's what's going on here. We have like the global, this is like all of the CPUs combined, and then we have the 4 threads that make up this. So technically speaking, I believe if you add all these numbers together, you should get this number up here. But yeah, we'll worry about this as we go along. So the first thing we need to do is we need to be able to parse this information. We want to get ideally these lines out of it, and we want to figure out what these numbers actually are. So here's the cool thing. We can get the man page here. We can man/proc/stat. Check this out. There we go. Now we have information about it. Kernel system statistics varies with architecture. Common entries include, and then it shows this. You can see like CPU 0 here. The amount of time measured in units of user hertz, 1/100th of a second on most architectures used, and then you can do this call sysconf to get the information to actually get the value that's relevant for your computer. We won't need this information luckily, but it just kind of tells you what's going on here. And you can see there's a system CPU line, and then there's a CPU N line where N is a number. So we had CPU 0 all the way up to CPU 3. We had 4 possible CPUs. That's what's going on here. And then it explains each field. So you can see we have this field, which is the user, this field, which is the nice. Then we have the system, the idle, the IO wait, and it goes on for a while here. As you can see, there's a lot of stuff down here. So we can use this to parse the information. Sometimes I've noticed some versions of Linux don't seem to like this man page when I actually just try to man this file directly. Take a look up here. You can see it's proc_stat, and it's in section 5 of the manual. So if yours doesn't work, you should be able to man proc_stat, and this will pull it up. If something weird happens, you can do man 5 proc_stat. Same thing. We're just going to tell it to pull up the 5th page or the 5th section of the manual. So this is how you can get this information if you're not able to get on your system and you're following along at home. So what does this get us? Let's go ahead and take a look at that file. So remember we catted it before, we got the whole file. Let's go ahead and run head on it, which will just get the top 10 lines. And we can limit this. Let's instead get the top 5 lines. The reason I'm doing that is because I know I have 4 cores. So we want the top line plus the 4 cores. That's what we're doing here. This is the information we're going to care about. Head -5 on this. And when you rerun it, you can see, okay, like we're just getting a bunch of numbers. What's happening here? Well, what if we ran it every second? So we can use the watch command to do this. We can do watch -n1 for 1 second. It will rerun this command every second and it will update. And as you can see, some of the numbers are changing, right? That's pretty cool, but it's a little bit confusing. Watch also takes another flag. We can give it -d, so it'll highlight the differences. So when we run this, we can see, oh, hey, take a look at this. Now we can see the differences here. It's still not super useful, but the point is you can see every second we look at this file, it's changing. This tells us the usage of our CPU over time. So this is since the system is booted. We don't really care about that. If we were going to write a program that shows visualization of usage over time, all we need to do is look at this number. We'll look at all these numbers technically. Look at all these numbers, hold that information for a second, look at all the numbers again, and then calculate the difference. Once we have the difference over a second timescale, then we know the utilization in that last second. If our CPU was, on 50% of the time and off 50% of the time in 1 second, that's 50% utilization right there. So that's how we can illustrate that. That's what we're going to use to get this information out of it. So let's go ahead and figure out how we're going to parse this, okay? Because we can, let's open up our script here. We have this. We can go ahead and make a function for gathering information. We could call it like read proc, and this will be responsible for reading that information. We're not actually calling this function yet. We're just sort of iterating as we go through. So we could do something like, cat proc stat. And there we go. Okay, it reads. It doesn't do anything with the information. If we were to call the function down here, it will just cat proc stat. That's great, but it's not really what we want to do. We want to be able to read this information in a way that makes sense. So what we can do here is instead of catting it, we can read it in a loop. We can do while read -r line, and then the done here will read in from proc stat. So we get rid of the call to cat. We're just using bash built in for this, and we can echo line here. So this is the same thing. This is the slow version. This is the very verbose version of doing this. But if we run this, we will get the same output. We're just reading the data line by line. So we can start using that while loop to actually parse the information field by field. So we just read it all in the line here. Well, we could read it into something like key, and then we could read it into, I don't know what the rest of the fields are, so let's just say foo bar baz. This will create new variables. So if we just echo key, and then we echo foo, and then we're just going to leave bar and baz alone. Let's just show it what this does. This will separate them based on the white space. So the cool thing about that is if you run this, you can see the key was CPU, and the first field that we named foo was this number. Well, that's useful. We just need to define all of the possible fields. So if we go to man proc stat here, you can see, well, there's a lot of fields here. User, nice, system, idle, IO wait, IRQ, soft IRQ, steal. There's a lot going on here. So we have to go over and we have to bring over these fields one by one. So to make this easy on myself, I'm going to do something new here. Not really new. I'm going to do something I don't do on this channel very often, but it's going to make a lot of you guys very happy. Check this out. tmux new. We're going to make a new tmux here because that way we can open up the script up here and we can open up another pane here. And let's move it down. This will probably be easier to see. Okay, now we can do man proc stat here, and we can get the fields down here, and we can move them up here. So we read the key. That's great. The next thing is the user, then nice, then system, then idle, then IO wait. So this is effectively creating new variables. We have a key variable, a user variable, a nice variable, and these will be set to each field of each line that we read. And each field is separated by every character that is in the IFS variable. This is set for us by Bash. We haven't modified it, so it'll be separated by a new line, tab, or a space character. This basically means any white space. So these are white space delimited fields, and as you remember from the output of the proc stat, that's how it's separated. So this makes it super easy to parse. So we just want to read key, user, nice, system, idle, IO wait. Let's go down here, and I think there's some more. IRQ, soft IRQ. What we can do here is we can put a nice little backslash, and then we can put a new line here, so we can just separate them so the lines don't get so gnarly. IRQ, soft, IRQ, steal, guest, and of course there's some more. Guest, nice, looks like the last one. Okay, let's do this. And there we go. That should be all of our variables declared. Now, we are in a function. So what we should do here, I'll go ahead and close this out for us. Because we're in a function, we should go back up here and we should declare them as local. So it's gonna be a lot of repetition here, but local key, user, nice, system, idle, IO wait, and then we can do this. We could also just declare these as local on a separate line. We don't have to do a continuation of the first line. IRQ, soft, IRQ, steal, guest, underbar, nice. There you go. So now we go down here and we can just echo, let's say we can echo the key and we can echo user equals $user, just to make sure that what we have here is sane and makes sense. So let's go ahead and run this. And what do we get? Hey, look at this. We have the user time for all this. Now, when we get down here, this doesn't quite line up. We're calling it user, but doesn't really make sense. We're only really cared about the lines that start with CPU. Those are the only lines we care about. So let's go ahead and filter for those lines. Now we could do the head -5 thing here, but this won't work on other systems where there's more or less than 4 cores. So instead we can just filter based on the key name. So we can just do a real quick check here. If key equal CPU star, so it's CPU and then anything else, then we care about it. Otherwise, we don't. So we can negate this thing. If it's not equal to CPU, then we do a really simple continue. We do the next iteration of the loop. We could technically break here because we know once we're done processing CPU stuff, we should go to the bottom of the file. And I think the file format is pretty safe. I'm just gonna put a continue here because for some reason, if the CPU line shows up somewhere later on the file, we'll still catch it. I don't think it really matters. I don't know exactly how stable this file format is, but I don't imagine it changing much in the future. But let's just put a continue here to be safe. So now when we run this, we're actually checking to only get the CPU thing. Say, look at this. This is awesome. We only got the keys that have CPU in them. So that's great. All right, so what do we want to do here? We have all of this data for all of the CPU keys. We know every single thing the CPU is doing. We know how much time it's spending in user time, nice time, system, idle, IO wait, IRQ, soft IRQ. We can condense this. We can get a very simple idea of what the CPU is doing by grouping them into 2 buckets. And the 2 buckets will be, are you busy or are you not busy? Are you busy or are you idle? So we're gonna go ahead and we're gonna use 2 new variables. We're gonna have busy and idle. Now the thing is, idle is technically already variable, so we're gonna conflate this variable usage. Just because it's simple, we already have it defined. But let's go ahead and add all these up. So it's gonna be a little bit verbose, but what I mean by this is we can say busy equals, and we can add everything together. So we're going to use this arithmetic expression for math syntax. And in order to determine if something is busy, we have to add all the things together where it's considered busy or doing work. So user plus nice plus system plus IRQ plus soft IRQ plus steal plus guest plus nice. All right, and for idle, we can just reuse the other variable that we already had, which was idle plus IO wait. So here we go. Busy is all the time the system was busy doing something, and idle is all the time the system was waiting. So now that we have this, we can print it out. No real reason to do this yet. We haven't done any math processing of the data, but we have it, so we can at least print it out to make sure it works how we expect it to. So hey, that looks pretty good. We get a lot of information here. Oh, am I still in Tmux? Ooh, that's weird. I'm gonna get out of Tmux because my muscle memory is totally gonna break. Okay, we're out of Tmux. Oof, that was scary. All right, so we run this. That's great. So we know how much the CPU was busy doing something and how much the CPU was busy not being busy. So not actually busy. How much the CPU was idle. Now here's the thing. We have this information, but we can't do anything with it yet because this is time since system boot. Instead, we're going to need to store this information and wait for a predetermined amount of time, let's say 1 second, and then get the information again and compare the differences. So let's go ahead and do that. All right, so first things first, let's figure out how to store the data. We can use an associative array. This is like a hash map or a dictionary or an object or something. It's a key value store effectively. So we can say data, we can declare this array as nothing. This is empty when it starts off. And then what we can do is we can store this data. So right here, we could say data, some sort of key equals some sort of value. Now we don't have the key and we don't have the value. Oh, actually that's a bad example. We do have the key. Look at this, I already named the variable key. Oh, it's like I was thinking ahead. Okay, so we do have the key. We just need to figure out what the value actually is here. Now what the value could be, there's all sorts of options here, but what we want to store is we want to store both the busy time and the idle time. Now we don't have nested arrays or nested data structures in Bash, so we just have strings. So for our value here, we're just going to store busy plus idle, not actually plus, strings appended to each other. So busy space idle. This way they'll be really easy to break apart when it comes time to do this. So we're gonna have busy space idle number space number. We should go ahead and declare value up here as local so we don't bleed into the global scope. And then when this is done, our data array should be full of all this information. We can print it down here. We can do declare -p on data, and this will print the data for us so we can see what's inside that array. So let's go ahead and run this and look at this. At the end of it, we have data set here. We have CPU 3 is equal to this, CPU 2 is equal to this, CPU 1 is equal to this, CPU 0, and then CPU without a number is equal to that. This is really cool. This is really good because we just need to do this twice. We just need to store the data, sleep for a second, store the data again, and then see what's going on. So the simple way, the naive approach, is to sleep one and then call read proc again. Now the issue with this naive approach is it's going to overwrite the data associative array up here. So we write into data, we sleep, and then we overwrite data. That's not what we want. We're gonna want two arrays here. We're gonna have one of current and one of previous, one of data and one of old. So the easiest way to do this will just be to name them very, very obviously. So we can have current is here, and then anytime we use data, we'll just use current. And then we will have a second array, which will be previous. And this is how we can calculate the deltas. So we want to read the proc, we want to sleep for a second, and before we read proc again, we want to store that data. We want to move the data that we have in current into previous. We want to copy data. So let's go ahead and make a function here called copy data, and then we will call read proc again. So let's go define copy data. Copy data, and we should probably do this just to be nice to our future selves. Take a look at this. Copy the data from the current array into the previous array. There we go, simple. So now we have a comment, we know what we're doing. If we're gonna do this, we're gonna be overwriting previous, we're gonna be getting rid of whatever's in previous. We should just do that manually here. We don't need the local keyword, we're referencing the global variable named previous. So we can just do this, and this will set it equal to an empty array. Now we just have to loop over all the keys in the current array and copy them into the previous array. So this is super simple. Let's go ahead and define key and value as local here. We're gonna do for key in, and this is our current one. To loop over the keys of an associative array, you might think you want the syntax, you actually want the exclamation here. So the exclamation tells it to loop over the keys of this array. You need this @ sign to do all the elements of the array. The exclamation tells it the keys. So now that we have the keys, we can go ahead and get the value out of it with indexing into the current array at value key with that $sign. It's very important. Now we have the value. So we can go ahead and set this into previous. So previous key equals value. Might be a little bit confusing, but all we're doing is looping over the keys of the current array and copying them into the previous array. So what does that mean? What does that mean when we are down here? Let's go ahead and declare -p. We're going to print it out of previous and declare -p of current. So when we go ahead and we run this, we can see that we will sleep for a second. That's great. Now we have two arrays here with very, very similar data, but the numbers are slightly different. This number in previous was what it was 1 second ago, and current is what it is now. Now this is super useful because we just need to calculate the delta for all of them. So let's do that. And before we do that, let's clean up some of the code we have here. Because we have our read proc, we have our sleep, we have our copy data, and we have our read proc. Let's go ahead and toss this into a main method just so we can kind of organize things. So there we go, there's our main method. And then down here, we will call our main method with all the arguments the user gives us. We're not processing arguments yet, but it's still good practice. All right, so let's think about what we have here. We have our main method, we read the data that's in proc, and we sleep for 1 second. That's great. There's not any processing we can do. We have to wait at least 1 second before we can start giving out some sort of meaningful information. Otherwise, we're showing the usage from system boot. So that's not entirely useful. So we read the proc data, we sleep for 1 second, then we copy it into the other array, then we read it again. Now we need to process that data. So we could just do this. We could say, draw bars. No, I don't like that function name. How about visualize data? There we go. So we just call visualize data and it will visualize it for us. And then we can kind of go into a loop here because we just need to loop all of this data over and over again. I'm assuming this program is going to keep running the same way htop runs. So where do we do that? We have our read the data, we sleep for 1 second, then we can go into our loop here. We could do a nice little while true, we will copy the data, read proc, visualize the data, sleep for 1 second, done. There we go. We can customize this as we go forward, but for now, I think this makes sense. We read the proc data first, no matter what, and we sleep for 1 second. We have to do that. There's no way of getting around that. Then we go into an infinite while loop where we copy that data over, we read proc again, then we visualize the data, and then we sleep for 1 second. I don't love that the sleep is duplicated here, but there's a reason for it, and I'll get to it towards the end of the video. So we have this. So if we run this, and let's go ahead and just define our visualize data function. So visualize data. Let's go ahead and just echo visualizing ... This is just a placeholder until we actually do it. Oh, I should spell this right, shouldn't I? Visualize data. There we go. So now we have that function. We've stubbed it out. We have visualizing. So if we run this, it should hang for a second, and then we should go into an infinite while loop of visualizing the data. This is great. This is awesome. Like, we just need to actually make it output something useful now. But hey, look at this. In fact, I don't even love that it has to hang for a whole second here. So we could go ahead and put something down here. I said it would be at the end of the video. I guess I'm just going to do it now. We can do this. We can say waiting for data ... Put that above the sleep. There we go. So when you first execute the program, you get waiting for data. Then we will visualize the data every second. So I think that makes sense. So let's go implement our visualize data function. We're going to go ahead and clear this out, and we're going to do something very simple here. We're going to loop over the array that we have. Now we have the current array and we have the previous array. It doesn't really matter which one we loop over. They should have the same keys because the keys were copied from one to the other. There could be a situation where they're not exactly the same. We'll get into that. I don't want to spoil some of the fun stuff in the video, but we'll loop over just any one of them because we'll get the same keys out of them. So we have for key and current. Now we need to call print bar on key. We'll go ahead and implement print bar later. Also, we're using the variable key, so let's go ahead and declare it as local so we don't bleed into the global scope. That's awesome. Cool. Let's go and define the print bar function now. So what do we have? We actually take an argument. We take key as $1. So this is the key into the array. This is the name of the CPU. Well, we have a couple bits of data here that might be useful. We have the busy time and the idle time in both the previous and the current. And with those two pieces of data, we can calculate the delta. So let's go ahead and store them. We're going to come up with really clever names for them. We're going to have busy 1 and idle 1, busy 2 and idle 2. There we go. We have previous and current. We're just going to use 1 and 2 here. So hopefully it doesn't get too confusing and bite us later. We're going to read out busy 1 and idle 1, and that is going to be read from the previous array at spot key. Okay, we're going to copy and paste that. I'm going to spell idle correctly because that'll be an issue if we don't. And we're going to read busy 2 and idle 2 out of the current array at array spot key. That's awesome. So now we can do some very simple and quick math. So to calculate our total busy or our delta busy, we just take busy 2 minus busy 1. There we go. And for idle, we do the same thing. We just do idle here, idle 2, and this is idle 1. There we go. So now we have the delta. We have in 1 second how busy was the system, and in 1 second how idle was the system. And we can also store another one, which would be total. So this is just both of these combined together, which is busy plus idle. This is the total amount of work that the system was able to do in 1 second. The man page goes over the units these are in. We don't really care about the units. We just need these numbers to calculate percentages. We want to know how busy and how idle the system was in a percentage sense or in a relative sense. So that's what this information is going to get us. So let's go ahead and calculate a percentage. So this is very simple. Perc for percentage. To calculate the percentage here, we're going to want to take, what was it, busy divided by total. So the amount that the thing is busy divided by the total amount of time there was will tell us how busy it was in that 1 second. And then if you want the percentage, you know that you typically divide it by 100. Here's the thing, we're in bash. We don't have floats, okay? So once you do busy minus total, there's a good chance that it gets so low that it's useless. So we're gonna wanna do things in a little slightly out of order thing. We can just do 100 times busy here. So we're gonna make the number get really big before we make it get small again. That way we're not gonna be in the realm of fractions yet. And I'll talk about that in a second. So let's go ahead and echo this. We can say key is %, %, busy. So there we go. Now we've implemented print bar. It doesn't technically print bars yet. We're not quite there yet, but we're looping over each key and we're calling print bar for each key, which is each CPU. So let's go ahead and run this and see what happens. All right, well, we get a division by 0. So that's not great. Thank you for breaking on that, Bash. I appreciate that. Let's go ahead and do some live debugging here because I don't know why this wouldn't work. Let's do a bash minus X on this and see exactly what it does. Okay, so bash minus X gives you the debug output. You can see exactly what's being run here. So we're calling print bar on this. That doesn't seem right. That's not what we want. We want the CPU key. We don't want the information here. So let's go ahead and look where print bar is being called. Hey, look at this, 4 key in current here. We actually want to loop over the keys and not the values. By default, looping over an associative array or any sort of array in bash actually loops over the values. We want the indices of the keys. We need an exclamation mark there. Now we can actually loop over the keys. So this should fix it. There might be other bugs, of course, but let's go ahead and rerun this without the bash minus X. And hey, look at this. That's pretty cool. So we can see each CPU has, let's make this a little bit easier to see. Where we call our visualize data. Let's put a final echo down here. This will just put a new line between each record when we sleep for 1 second. So you can see, okay, they're grouped by 5 because there's 4 cores and then 1 global CPU key. And it tells you how busy it is. Now this machine is not very busy, but there's a couple things to note here. First of all, let's go pull up htop. Htop gives me this nice little fractional thing. As you can see here, we go down to 1 little fractional level there. It'd be nice if we could do the same thing in bash. So let's go ahead and do that. Now, like I said, bash doesn't have floating point values. It's not great, but we can do some trickery here. Instead of 100, let's just do 1,000 here. Now, we're gonna call it percentage. It's not technically percentage, but watch this, watch this. When you run this, you can see that, oh, look, this is 20% busy. This is 9% busy. That's a lie. When it says I'll stop the output. When it says it's 19% busy, what it means is it's actually 1.9% busy. So we can create that output. We can handle that output ourselves. So I'm going to rename some variables here. We call it perc. It's not really a perc. We're going to call it usage. This is how much is being used in that time. So we have the usage now, which is a number out of 1,000, which tells us basically how much is being used. We need to turn that into a percent. So what we can do is we can get the integer side and the fraction side or the decimal side of it. So we could say local int equals, usage divided by 10. So this will be a number out of 100. This is the integer side of it. And then we want the opposite side, which is the fractional side or the percentage side or the decimal side. So we'll put frac here for fraction. And instead of divided by 10, we're going to modularly divide it by 10. That means divide by 10, but keep the remainder. So in the example of 19, we're going to do 19 divided by 10. That'll bring us down to just 1, because it'll chop off any sort of remainder. It'll be 1, and then this fractional portion, 19 modularly divided by 10, will be 9. So we'll have 1 and 9. We can put them together with a period between them. Now we have 1.9. So there we go. That's pretty beautiful, actually. So now we can do perc equals this, which is just int dot frac. The dot is just a literal dot. So now we'll leave everything exactly the same. We'll rerun this script, and we'll see what happens. Hey, look at this. Now we have fractions. We don't have floating point numbers in bash, but hey, we pick a little fixed point and we're kind of good enough to go. So yeah, pretty beautiful here. So one thing we can do here is this is a stylistic choice. This is a choice that I'm going to make because btop does it one way and htop does another way. Htop only shows the chords. It doesn't show a global CPU key. Btop does, but I'm going to go ahead and say we just filter it out. Let's go ahead and filter out the key that is exactly CPU. We don't care about the global state of the CPU. We just want to see the threads, the cores. We just want to see the actual core usage. So let's go ahead and go back up here in read proc where we filter it out. And we say if key is not equal to CPU star, then continue. That's great. We can do an else here. We could put it all into one line if we wanted to. I think the else will just make it simpler to read. Else if key equal CPU literally, then continue. We can do that. So filter out everything but the cores. There we go. Very simple. So now if we rerun this, look what's going to happen. We have just gotten a syntax error because apparently I can't program. Oh yeah, because I put else. I wanted elif. There we go. That's Bash's version of else if. Let's go ahead and rerun that. Let's do some movie magic, edit that out. Look, I never make mistakes when I program. And there we go. Look at this. So now we're just getting core usage on our machine. So that is really, really cool to see. Now that we have this, maybe we should actually start visualizing it. What do you say? I mean, the whole point of this video was to visualize CPU usage, and we're pretty far in. So let's, a lot of setup there, but let's go ahead and actually start visualizing it. So in our print bar function, we have the percentage, we have the usage amount. That's really great. How can we print a bar? Well, here's the cool thing. If you remember previously on this channel, I made a video about making a progress bar in Bash, and I have that code. I'll show you guys an example from the video, but as you can see in my YSAP directory, this is all available online. People can check this out. I keep track of all the code I wrote for different videos. So in here, I have a progress bar code. 2025, August 21 looks like when it went up. So we have a progress bar here. If we run the progress bar code, look at that. That bar is pretty much what we want. Now, it ran really, really fast, but that progress bar, that bar logic is what we want. So let's go ahead and just yoink that. Let's just take that. We have this whole little progress bar function here. We can take that and use it and make something cool from it. So let's go ahead and vim that progress bar. Let's also vim, I have to remember where I was before. I think I was in viz. Yeah. So we'll vim this. We'll grab the stuff that we care about here, and we will just copy all of it over here. So I've just brought this into the new file. It might be a little bit confusing. Don't worry. We'll walk through it step by step because it's not going to work as is. We're going to have to make a lot of changes to it. So here is the print bar function. We are back in the CPU script, and you can see we do a lot of logic here. This is where we previously ended, and then this is all the stuff that has been yoinked from that file. So we've yoinked some stuff. Let's go ahead and do something with the yoinkage. The yoinkage, dude. I'm just making up words. So we're going to do a little bit of cleanup here. Let's go ahead and just get rid of some of these variables and hope we don't break anything in the process. So here's our bar character. It's a nice pipe character. Here's our empty character, which is a space. Here's the length. This is the length of the bar that we're going to print. We've chosen 50 characters. We'll modify this, of course, but for now we're going to leave it at 50 just to get something done. And now we have the % done. This is how much is done and the number of bars we need to print. Because again, if we're only 50% of the way done, we only want to print like 25 bars if we're doing a length of 50. So that's what's going on here. So as you can see, we have perk done is current times 100 divided by len. We don't have these variables anymore, but as you can see, perk done is only used in the output that we print here and up here. We already have the perk that we care about, which was just perk. I know these variables are confusingly named, but what I mean by this is we can just trash this. We just need to come up with the logic to figure out the number of bars we should print. So here's the cool thing. We know how much we've used on the machine. Remember we had that variable called usage and it was out of 1,000. So this variable usage is out of 1,000 and tells us how many bars we should print. This is how busy the CPU is. So we can do usage times length, which is the number of bars we want, divided by 1,000 because 1,000 is the number we chose to use up here. So we do usage times length. We get the bigger number first because again, we don't have fixed point. We don't have a floating point arithmetic in Bash. So we take our usage, which is that number between 0 and 1,000. We multiply it by length. This is the number, this is the size of the bar that we're creating. And then we divide it by 1,000, which is that arbitrary scale we've chosen. So with that, we should be good to go. All right, so the rest of the code might be confusing if you haven't watched my first video on progress bars. I would say go check it out. It's a really fun watch. It got a lot of people over to the channel, so that's why I like revisiting it when I can. So as you can see right here, we create a new string called S, which starts with the left square bracket. So if you remember that progress bar output, it starts with this left square bracket. It prints a bunch of bars or space characters, and then it prints the right square bracket and then some metadata information about it. So that's basically what we have going on here. We create a new string with the left square bracket. Then we start I equals 0. I less than the number of bars we should print, we append a single bar character. Then, after we've appended all the bar characters we need to start at the number of bar characters we omitted. So imagine if we were going to print 50 of them and we only wanted 20 bar characters. After we've omitted 20, we start at 20 all the way up to 50, we put an empty character. So this fills the rest of the progress bar, or in this case, our usage bar, with spaces effectively. And then when we get out here, we just print the actual data itself. Now we're putting a \r here because the progress bar needs to overwrite itself. We don't need that anymore. We can get rid of the -e, we can get rid of the \r here, and we can get rid of the -n, which doesn't emit a new line. We actually want a new line here. So let's go ahead and do this. We'll do S, which is our bar. We have current out of len. We don't need that. We just need the %. We already have that. In fact, the one last thing we should put here is the key, which was the name of the CPU. So this might be a little bit confusing, but all at the end of everything here, we just echo $S, which is the bar, $key, which is the CPU name, and $perk, which was the percentage. So let's go ahead and run this and see what we get now. So clear the screen, run CPU, and look at that. Look at our beautiful CPU usage graph. Now you might notice something. The system's not doing anything. The system is very idle. That's not a mistake with the code. It's just look at htop. Like nothing's happening here. There's not much happening here. So what we can do is we can make something happen. All right, we're gonna fabricate some busyness on the system. So if you watch my video where I talk about GitHub safe sleep script, we're gonna go ahead and re-implement that ourselves. And what that means is put our system into busy wait. We're gonna make our system busy doing nothing. So let's go ahead and run our CPU script up here. And let's go ahead and run a very busy program that does nothing. So what does that look like? While true, do, true, done. An infinite while loop in bash that does nothing except eat up system resources. You ready for this? Run this. And look at that. Look at that CPU usage. As you can see, we've completely pegged one core here. That's what's going on here. So this is just sitting on one core, just locked on that core, doing work. When we control C, it's gone. Hey, that's awesome. But when we go ahead and run it again, you can see we are just absolutely slamming that core. So this is cool to see. It's working. We've actually made something here. We've made a visualizer for CPU usage, just using bash built-ins and the proc file system. So that is really, really cool. Of course, still more work. There's still a lot of things that can be customized with this. I think the first thing that jumps out to me is look at the order of things. CPU 3 is at the top, CPU 2, and then CPU 0. Seems kind of backwards, right? Wouldn't it be nice if we could just like sort that data? Well, we can, and it's a little bit different than you would expect. Because then, like, look over here in htop, it's 0, 1, 2, 3. So it goes in opposite order. I would like it if it was ascending. In bash, we don't actually have a good built-in way to sort things, okay? We could pipe out to external utilities like sort, and we could do some work there, but we don't have a good way ourselves to sort things. So instead, what we're gonna do is we're gonna take advantage of the fact that the CPUs are numbers. I'll show you what I mean by that. So let's go here. We have our main method that calls read proc. That's where we actually load up our two arrays here. We have our two hash maps, our two associative arrays, and they get loaded up by the read proc function. So the read proc function takes the $key, which is the CPU name with the number, and then it stores it as the value. Well, here's the thing. It doesn't just take the CPU number. It actually takes the raw string of CPU 0 or CPU 1 or CPU 2 or CPUN. We can get rid of the CPU prefix. We could be left with just a single number. So this will work for us. Let's extract the number. We'll make a variable called num here. Once we're down here, we know it's a CPU. So we can do this. Num equals key, # CPU. That's it. This tells bash from the left-hand side, find the string CPU, just the literal string of CPU, and delete it. So this just removes the literal string CPU from the left side of the actual string that's in key. That's all we need here. So then when we store it here, we just store it as num. That's it. That's all that's needed there. So when we run this, it's still gonna be out of order, but take a look at the data we get now. As you can see, we don't have that CPU prefix. We just have 0, 1, 2, and 3. Okay, that's a great start, but what do we do here? Why do we bother doing that? Well, think about it. Our key name now is a number. It's just a number, meaning we don't need these to be associative arrays. They could just be indexed arrays. If we get rid of the -a here, they are just indexed arrays, meaning the key is a number, and we're giving it a key that's a number. Now, we might be giving them the keys out of order. In this case, I don't actually think we are, but if we were, it's not a problem. Bash has sparse arrays, meaning if I make an array in bash, like, I'll make one on the command line here, foo bar baz, and then we do a declare -p on array. Oh, wow, we're in tmux still? I keep forgetting when we're in tmux. If we do a declare -p on array, you can see 0 is foo, 1 is bar, and 2 is baz. We can also do array 45 equals high. and then we will also have a key called 45. So Bash is okay with this. It's okay with sparse arrays. The numbers don't have to be contiguous. So this is good for us because we don't have to worry about what order we read the CPUs in. Again, I think we're reading them in the correct order. I don't think it really matters. But if we get rid of that dash capital A, everything should just work. It should just work. We're loading them into an indexed array, and the keys of indexed arrays are sorted for us. That's the kicker here. So when we run this, let's see what actually happens. Look at this. Now we're sorted. 0, 1, 2, and 3. That's really great. If we wanted that information back, we could print it back. So let me go down here to where we actually print the bar. We print the key here, which is the number of the CPU. We could literally just put the string CPU before we print the $key down there, and that'll work because we're just changing what we display to the user. So there you go, CPU 0, CPU 1, CPU 2, CPU 3. So yeah, very simple, but that's how you would do that. So now, here's everybody's favorite time, okay? We're gonna make this fancy. We're gonna add some color output. We're gonna do some real fanciness here because take a look at htop. When I run htop, you notice what happens? Completely clears my screen, shows me this nice visualization, and then when I close it, it's gone. It's gone. When I run btop, it shows me this nice, beautiful TUI, this nice, beautiful terminal user interface. When I control C it, it's gone. It's completely gone. When I run ours, it shows it right to the output, and when I control C it, it's still there. There's nothing wrong with this. This is totally fine, but we could make this act more like a TUI, like a terminal user interface. And before I continue, I'm on fire, so I'm taking this off. All right, that's much better. So there's a couple ways we could do this. I've used the tput command in the past to run ANSI escape sequences. I've also hard-coded them. I figured for this one, we'll just hard-code them. It's kind of fun to actually show the process of looking these things up. You could use the tput external command if you wanted to, but let's go ahead and just hard-code some ANSI escape sequences. It's nice to see actually just kind of what's going on and how they work. So I've showed this before. I really like this. This gist by FNKY or Funky. I don't know if that's how you're supposed to pronounce their name. I like this gist. It's ANSI escape sequences. It's kind of funny that my go-to reference for ANSI escape sequences is just a gist on GitHub, but it is, and I really like it. So there's a bunch of cool stuff you can do. This is how you output like color to the terminal and stuff like that. It shows you all different fun things. But this is what we're going to want. I like this little screen right here. So this is going to give us things like make the cursor invisible, restore the screen, enable the alternative buffer, disable the alternative buffer. So we're going to want some of these things. So I'm going to go over back into our code and we're going to do some magic here. So in our main method, all the way at the bottom, we read proc, we echo waiting for data, we sleep for 1 second. Once we have the data here and we are ready to start going, we should configure the terminal for drawing. So that's where we will put these sequences. So we should enable alternate buffer. We should hide the cursor and we should move the cursor home. This last part is technically optional. I think when you enable the alternate buffer, it puts the cursor at the top. It gives you a nice clear screen, but we can do that here just to be safe. So enable the alternate buffer. We can do that with a nice little printf. Let's go ahead and take a look at what we have here. Actually, if we pull up the thing right here, okay, enables the alternative buffer. We need this. I'm gonna go ahead and copy this over and I'm gonna show you what you actually do with this information. So we have this, we're gonna put it in a printf in a single quote. And there you go. The only thing we need to change is this ESC. This is the ANSI escape code. This is the ANSI escape character. It's a single character and it's like hex 1B or it's octal 33. We can get it with a \E. So if we put that \E there, this is the escape character and this whole thing is the escape sequence. So this will enable the alternate buffer. Then for hiding the cursor, it's very much the same thing. I'm just gonna go over and look at what it is. Make cursor invisible. Yes, I'm just going to paste this from the other screen. I know you guys can't see it, but take a look. This is what it is. So we just need to get rid of this ESC part because that's what the escape sequence is. And the final thing would be to move the cursor home. I'm just going to put the escape character there. We don't even know what it is yet, but let's go find that because there should be characters. I forget where they actually are, but there should be things to jump the characters all around. Here we go. Move cursor to the home position, 0, 0. So very simple. It's just a bracket and then H. That's a simple. There's all sorts of fun things here. You can move the cursor all around the screen and do all sorts of fun stuff. All we need is this bracket H. So let's go ahead and pull that in. So we do a nice little bracket H here. And there we go. Enable the alternate buffer, hide the cursor, move the cursor home. This is great. The problem is when we're done and we control C it, we're going to be stuck in the alternate buffer. We're just going to be stuck with the cursor hidden. That's not great. That's not what we want. So before we do this, we need to get the terminal ready for not drawing. We need to clean up the terminal when this script exits. So we can do that. We can trap, which will allow us to hook our code into a signal. The code we're going to hook up is the cleanup function. We haven't written it yet, but we're going to hook the cleanup function up to the exit signal. This is a meta signal in Bash. Bash will run this at exit. If you ever run like a C program or something, you have at exit. This is what it's going to get hooked up to. So we can go ahead and define our cleanup function here. And this is where we will need to undo most of this stuff. So let's bring this code down here. Let's put it here. We want to disable the alternate buffer, and we want to show the cursor. And I will show you the codes for that because these codes aren't technically right. But go ahead and take a look at this. See how there's an H here and an L here? Here's just like a fun little trick I'll show you. So when we go back here, we scroll down to that section that had everything we want. And by scroll down, I mean I always forget where it is. Here we go. Make the cursor invisible. Well, we want the opposite. We want to make the cursor visible. So the L becomes an H. And then when we want to disable the alternative buffer, the H becomes an L. It's the only difference there. So one is an H, one is an L, and when you want to do the opposite, you just swap them. A little bit weird, but yep, so this H becomes an L, and this L becomes an H, and there you go. We've disabled the alternate buffer, we show the cursor, which is the opposite of enable the alternate buffer, hide the cursor, and then of course we move the cursor home. So if this all works as we expect it, we should be able to run this, and let's see what happens. The whole screen should look like it clears. There we go. We have this. It's still printing new stuff. When we Control C, it brings us back here. Hey, how cool is that? That is awesome. So of course, there's one last thing to fix here is when we draw this data, we probably want it to overwrite what was already there. We don't want it to keep printing new things to the screen like this. So let's go ahead, let's Control C, let's get out of there. And then right here, we copy data, we read proc, we visualize data, and then we sleep for 1 second. Well, what we could do here is we could very simply clear the screen, but we don't need to actually clear the screen. We could just move the cursor back home. We've already done this. Take this logic right here, move the cursor back home, and then visualize the data again. Might be a little bit confusing, but let me show you what happens when we move the cursor back home. Look at that. We are just overwriting the data. It might be hard to see. Let me go ahead and split this terminal again. So now, while this is running up there, we can do that while true, do true thing, and this will just completely peg one of the CPUs. So there you go. You can actually see that we get like live feedback of it when I Control C, then it goes back down. So it's updating in place right there, which is really cool. When I Control C it, we're done. That's really awesome. Did you notice a problem with it? Here, let me show you that problem again in case you may not have noticed it. All right, so I'll run CPU up here, and then we'll go back down here, and we'll do our nice little busy wait. And this will peg one of the CPUs. So as you can see, CPU 1 is now at 100%. And let me go ahead and Control C that, but look at this line, okay? See all those percent signs there? It's not great. The reason that's happening is because we're not actually clearing the screen. We're just moving the cursor back to the home position, and we're overwriting everything. Now these are all being overwritten by spaces, so that's really great. But this isn't really being overwritten. So we might actually benefit from just completely clearing out the screen before we draw it. We could get some tearing artifacts that way. There's a bunch of ways we could handle this. I'm going to opt for the simple solution. So I'll show you what that looks like. Let's go ahead and Vim this program one more time. Instead of moving the cursor home, we can just clear the entire screen. Now there's a really simple way. Obviously we could just run the clear command, and that totally works for us. So we pull back up the reference. You can see here there's a whole bunch of different ways to erase the screen, but take a look at this. Erase entire screen. Escape bracket 2J. So if we just run that, we can run that right before we do anything. So right here, before we move the cursor home, we can move the cursor home, but before we do that, we can clear the screen. We can do, what was it, bracket 2J. So clear the screen. I think this has the same effect as moving the cursor home. I'm gonna go ahead and comment this out and just get an idea and see if that's the case. But let's see. No, it doesn't. No, it doesn't. Glad I tested. It looks so stupid. All right, let's go ahead and move the cursor home after we clear the screen. Oh man, that's funny. Okay, so there we go. That's nice. The one last thing we could do is if you take a look at this, we clear the screen and then we call visualize data. Now visualize data is pretty fast, but it could take a long time. There is another way you could get around this. We could just make a variable called S. We could say S equals visualize data. We could call it like this and store it into a variable, and we could put it up here. So we can call visualize data. This is the heavyweight function that'll take a long time to visualize the data. This one's pretty fast, but this will visualize the data for us, store all of that into a variable called S. Now we can do all this very quickly. Now that we've done all that heavy lifting, we can clear the screen, move the cursor home, and simply output that to the screen. That's it. So let's go ahead and run this and see what happens. It should look the same, or we get a syntax error, right? Yep, that makes sense. We get a syntax error because you have to put a $sign here. There you go. That's what I forgot. This is yelling at me. This is relatively new syntax for Bash. This was introduced in Bash 5.3. So as you can see, my syntax highlighter with Vim does not like it. I bet if I were to update Vim, it would probably be okay with it. But right now, Vim is yelling at me. It's telling me this is not valid. It is valid. I will prove it to you by running it here. And there you go. So what's happening is that heavyweight function of displaying all the bars is being run and stored in a string. Then we're clearing the screen, moving the cursor, and echoing that string to the screen. That part's really, really fast. So this should eliminate any sort of like tearing or blinking that you might possibly see, or severely cut down on it. Again, it's not much happening here, so what can I do? Can I just do my little, oh look, even just the act of creating that did that. So we can just do our busy wait loop here, which is this. And there you go. You can see that one CPU starts to get pegged. That's awesome, that's great. Okay, I'm probably gonna cut this from the video, but if I do like a VPM upgrade, I wonder if it'll pull in like of Vim. Yeah, because as you can see, there's a new Vim here. Is it pulling in a new version of Linux? If it's pulling in a new, oh yeah, no, I don't want to do this. It's going to pull in a new version of Linux kernel. That seems like too much work. Nah, it's going to want to do everything. XBPS, install Vim. There we go. Why is Vim installing Wayland on a headless server? How does that make sense? I don't know, man. Linux is the Wild West. All right, I updated Vim and apparently installed Wayland, dude. I don't understand what Linux does. Do you think it's going to give me better syntax highlighting? Hey, look at that. There we go. So yeah, if your Vim's yelling at you, just upgrade Vim, and apparently that just fixes this. So that's fun. That's awesome. Good, because I knew it was valid syntax. It's valid for Bash 5.3. The output is a little bit bland still. We have the bars. We have that. We could put a little header at the top. Nothing too fancy. I don't want to go over the top here, but we could do a very simple header. We can put that in visualize data. So visualize data here could also just print out something at all. Also, I just realized we don't print anything at the bottom, so I think this bottom echo is not necessary. Let's go ahead and delete that and just run it again and see. Yeah, cool. So I believe the cursor is here. Well, that's not good when I start clicking things. I believe the cursor is here because we don't emit a new line as opposed to being down here. It doesn't matter, the cursor's hidden, so who cares where it is. But yeah, let's make this a little bit fancier. We could do something like this. Echo CPU usage on host name. There you go, very simple. So now if we rerun this, we can see that we have a nice little line at the top. CPU usage on void.rapture.com. Cool, that's the host name of my machine. Hey, that's pretty cool. We could also print out maybe like the date or something if we wanted to. So you could do this. Echo -n this, so -n removes the new line that Echo would normally emit. Then we could put the date here, so you get some behind the scenes information here. You can see that I'm recording this on January 13th. That's pretty cool. We do have to fork out to date every time, so of course we're on Bash version 4 and we're on a very new version of Bash, so date is actually built in to Bash. We can just use printf. So printf takes a bunch of different format specifiers. It takes this new one called %t. I say new, I think it's like 15 years old. And %t takes a number here. This is an epoch time, so like, you know, a Unix timestamp. But if you give it -1, it will use the current time. In fact, -1 is the default, so if you give it nothing, it will use the current time. Now, it will yell at you because it wants something between the % and the t. In parentheses, you have to now put a stirf time formatted string, or a stirf time. So if you do man stir f time for formatted strings for times, you can go down here and you can see that there's all sorts of percentage things you can do. So like this is the hour as a decimal number. This is the hour of this. This is blah, blah, blah. There's a ton of stuff you can put in there. So we're going to go ahead and put a very, very simple string in there. So I did a quick Google search for, what is it, ISO 8601. This is a pretty standard date stamp format. And as you can see, go down here. This one's specifically for Python, but it doesn't really matter because stirf time is stirf time no matter what language you're in. So we're just going to copy this and we're going to use it. That over here and put that in between these two parentheses. That might look insane to you, but I promise it's real and it works. Now printf doesn't emit a new line by default, so we could put a new line here, or we could just put an echo down here for a new line. So I'll show you what this looks like when we run it. Run this, and now you can see, hey, look, here's our time here. Now this %f, oh wow, every time I click and drag, it kind of really messes things up. As you can see, that %f doesn't seem to like that. Doesn't look like we have that that part of it. Let's just go ahead and cut out some of that. There you go. And cool. So now you can see here's the actual timestamp. So that's pretty cool. It's like embedded the actual time zone data into it, which is pretty neat. So yeah, that's awesome. We could clean this up a little bit more. As you can see, we do printf. We printf directly to the screen. We don't have to do that. We could store that into a variable. -v now means to store it into the now variable. So let's go ahead and declare that as local. So now we have the current timestamp. So instead of doing all this, we could bring it down to one echo statement. I think this is a lot clearer to read. So the header is one echo statement where it'll just have this. It'll look exactly the same, but we're just storing it in a variable and then formatting it with the echo statement. So there you go, CPU usage on void, and we have this right here. Okay, cool. It's very simple, very nice. Let's go ahead. It's still really boring looking, so let's colorize it a little bit. I think we can make this look a little bit nicer. In our print bar function, we have our bar char, and our empty char, and our length. So let's go ahead and do some things a little bit different, okay? We have these three things. Let's bring them to the top. We have our bar char, our empty char, and the length. Let's go ahead and define them globally. So we have our bar char, empty char, and length. Let's call this bar length just because it's easier to understand. And then of course we want these to be global, sort of unchanging. So let's make these all uppercase. This is just a convention, so we know what's going on here. So we have bar char, empty char, and bar length. Let's go out here, find the length is 50, change that to bar length, and change that to bar length. Cool, we don't use it anywhere else. Let's get rid of bar char here and empty char. Let's get rid of this comment that we don't need anymore here. It's fine, bar char is there, so that'll be bar char, and then empty char. I think we only use these once. Oh, that's so convenient. Empty char. So there we go. That's awesome. If this all works, it should still work exactly the same. It shouldn't look any different. We haven't actually modified anything. We just moved to a global variable. The reason we do that is because now we can modify this. Look at this. We have a pipe character here. This doesn't have to be a pipe character. It could be anything else. But you know what else it could be? It could be a special character. It could be an ANSI escape code. And we could say 33M and then a pipe character. And then it could be an ANSI escape code. And it could be 0M for resetting it. Might be a little bit confusing, but let's go ahead and see what this looks like. Let's pull up a new tmux. Oh, we already have tmux running. Oh, that's awesome. Let's go ahead and run this in tmux. And the reason we're doing that is because we can go over here, open up a new one of these. Oh, you can see it already. Spoiled it. Let's go ahead and put one in a busy wait. And look at that. Now it's yellow. So we at least have some color output here. It's not the prettiest thing in the world. We could obviously customize it way more. We could customize the CPU color. We could customize the percentage. All sorts of fun thing there. We could customize the percentage if it's over like 5% and we wanted to warn the user or something like that. We could draw these bar characters in different colors based on what kind of usage it is. There's really no limits here. I kind of want to give you like a jump off point or a starting point for this, but take a look at this. We got some kind of fancy output here. Okay, I actually said I wasn't going to customize it, but I feel like it'd be a lot more fun if we customize it, wouldn't it? I think it would, so we should go ahead and do that. Now there's all sorts of different ways to approach this. I'm going to pick a very simple way of approaching this. We're just going to make a couple different color variables that we can use here. Nothing fancy, no real rhyme or reason for this, but we can just define some colors here. So we can have like color 1, color 2, and color 3. Again, no real rhyme or reason, just different colors. We're just using basic 8-bit coloring, and as long as we have a reset color, which is just the 0M there, hey, that makes perfect sense. Let's change this bar char back to just a pipe character, because then we will colorize everything inside print bar. So inside print bar, we could do something like every time we append a bar char, we'll actually just give it color 1, the bar char, and then the reset color. And then down here where we print like the CPU name, we could do color 2, the CPU. We have to put these in curly braces because we don't want the actual string. We want the string CPU to be the actual string CPU. And then here we could do reset. And then for the percentage, we could do color 3. And then the percentage, and then put a nice little reset here. We can see what that looks like. We're just kind of messing around right now. And I actually have no idea what this will look like. Well, that's kind of cute. The CPU colors are like magenta, and then you have like this nice little cyan color. And I think the, what does it get if we make the busy wait loop? Oh, okay, it's a nice little blue color. I mean, that's kind of cool. Again, random colors, just kind of fun to stylize. Yeah, I don't love that it's blue. Blue doesn't appear to me like it's doing anything. So let's do 31, which is red, I think, right? Because red kind of makes sense. Like, oh no, your system's busy, it's red. Like, yeah, that makes sense. I know htop has red and green is different for like user and system time. We haven't gotten quite that fancy, but we can just have red for usage. We can have a nice little magenta color for the CPU name, cyan for the percentage done. That's pretty cool. The other thing we could do is we could change the header that we print. We could probably make that a little bit fancier. I kind of like this. We could add a new color. We could just add dim. I like this one a lot. Dim just makes it dim. Some terminals don't support this, but what I like here is where we do our header, where we print like the host name and stuff. We could just put dim in front of it, and then we could reset it right at the end. So reset, there we go. Let's go ahead and run that and see what happens. And then you can see, okay, we have this nice little thing here where it's a nice little grayed out line. We don't really care about that line very much, but we can see that we have the CPU usage, we have all this, and then we have that. In fact, oh man, this is how it happens. This stuff just starts getting like feature creeped a little bit. I actually kind of would rather it be like this. All right, hear me out, hear me out. We're going to take the date out from here, and then we're going to move the date logic down here now that we're at the bottom, and get rid of this, get rid of this. Just print it to the screen directly, and we probably do want some dim coloring, so I'll go ahead and add that stuff back, and now we can do this. Echo dim now reset. There we go. We don't need these curly braces. There we go. So we'll put the timestamp at the bottom of it. Okay, so this will look kind of cool. We'll have the header at the top, CPU usage on void.rapture, and then we have the timestamp at the bottom of it. So hey, this is pretty cool. Like I mean, you could spend a lot of time on this. I probably won't spend any more time on it. Okay, I lied. We're gonna spend a little bit more time on this. Check this out. What if we do like color 2 here or something, right? It's still gonna be dim, but look at that. That is really cool. Okay, I think color 3 is actually gonna be good. Oh, I wonder how much of this I'm going to cut from the video if you guys are going to see this whole thing. It's just fun. It really is fun to mess around. Okay, that's really cute. That's really cute. I even like the dim color there. That is awesome. So yeah, let's go ahead and open up a new thing. You can just see like some of the red show up. Hey, that's pretty cool. Look at that. Oh yeah, look, color's just great. It can just make things so fancy. I love it. That's awesome. Now we should do something before we move on here. We should make the color a little bit customizable. And what I mean by customizable is you should be able to turn it off. So I don't know if you guys have seen this website, but I want to point this out to you. This was pointed out to me a couple of years ago on one of my open source projects. Take a look at this website, nocolor.org, okay? No color, an increasing number of command line software output ANSI color escape codes, and that's great. I'm not going to read the whole thing, but long story short, there should be a way to turn this off. And I completely agree with this. So there's a lot of specifics on here. There's a lot of information here, but basically the idea is that it's proposing a no color environment variable to be able to turn off color output. There are other ways. Obviously, we can check if the output's a terminal, although we are kind of running a little bit of a TUI. So if your output's not a terminal, you know. But look at this. The idea is by adopting this standard, users that prefer to have plain non-color text output can export no color equals 1 to their shell's environment and automatically disable color by default in all supported software. So I like this. I think that makes sense. I think this makes perfect sense. So as you can see right here, if no color is not equal to null and no color is not equal to the empty string, then color equals false. So the idea is that you assume color is true. You assume it's true unless no color is set to anything. This is the idea. Not just that it's set, but that it's set to anything. I think I might be being pedantic here, but it's set to something. So what we can do is we can go over here into our code and we can be good here. So we could check this. If -n no color. That means if it is set and it is set to something, it can't just be an empty string. It has to be set to something. Then we will initialize all these colors. That's super great. Otherwise, what we will do is we will unset all of them. We will treat them as though they are set to the empty string. So we'll just trash all these. And if you wanted to save room, you could put them all on like a separate, you could put them all on the same line like this. We can just do this. There we go. So now we will honor if the person does not want color output. So if you run CPU on your own, you're going to get color output. Or I got that wrong. What did I do wrong? Did I have that set? If -n no color. No. I got this wrong. I got it backwards. If -n no color. That means the user doesn't want color. So what do? I set color for them. Okay, well, we got that completely backwards here. I could swap these two, or I could do this. I could say -z. -z means that it's not set, or that it's set to an empty string. So -z, no color, that means this environment variable has nothing set in it, or it's set to an empty string. Then we're going to set the colors to what the user wants. Okay, yeah, I got that a little bit backwards. My bad. So if we run this, now we have color output. That's great. If we run it with, oh, I'm in Tmux. Oh boy, that always throws me off. No color equals 1. If we run this, now we have no color. So that's really cool. I like that a lot, because this way we allow the user some control over this, which is pretty cool. All right, there's another thing I want to work on here, which is the length of this this progress bar. Nope, let me try that a third time. I want to work on the length of this utilization graph right here. I guess it is a graph, whatever, I don't care. we have this hard coded to 50. So as you can see, there's 50 spots here, plus the bracket and the bracket, plus the text here, plus the percentage here. So wouldn't it be nice if this could grow or shrink with the terminal? Because right now, yeah, we have it set. You can modify this yourself. We have this bar length of 50. We could set this to like 80 and then rerun it. And you can see that now it kind of overflows to the next line. It's not great, but we could do something like this. Well, the nice thing is we actually have the options in Bash that we care about. We have shop-s check win size. This will turn on the ability for Bash to determine the window size. And this gives us variables like columns and lines. So we know how many columns long the terminal is and how many lines there is. Columns is width, lines is height. So columns 86, that's great. We need to draw up to 86 characters on a line, and then we can make this thing grow and shrink with the terminal. So here's the obvious thing we can do, right? We can go here, and where we have our bar length, we have it set to something up here like 80. We could just change this to be the number of columns. Now, we haven't turned on check window size here yet. So what we could do is we could set bar length to some sort of thing like 30, right? Some sort of sane default. And then when we go down here, after we turn on check win size, we've done all this stuff. Now we could say something like if -n columns, that means we know how big the terminal is. Then we can say bar length equals columns. So that's really good. So if we know how many columns there is, we'll set the bar length equal to that. Otherwise, we'll default to our sane default of 30, right? So if we run this, what do you think is going to happen? Well, not great. We try to draw the exact length of the terminal number of characters, but then we still have more. We have the square brackets, we have the CPU identifier, we have the percentage sign. So we have to subtract something from it. Now, how much do we subtract from it? Because, you know, it can get a little bit confusing here. Let's think about it. What we have to do is we have to come up with the worst case scenario that we have to subtract from it, okay? This will be our buffer size or our screen buffer size. So what I mean by that is we always have to draw this open square bracket. We always have to draw this closed square bracket. That's 2 characters right there. This space is 3. The string CPU is another 3, so that brings us up to 6. Okay, now we have a number here. This could bring us to 7. It might bring us to 8, 9, 10. We don't know how many CPUs there are. We have another space. We have another percentage. It goes up really high. So we have to come up with the worst case scenario. So let's do that. So we have this right here. Instead of putting this hard-coded here, we'll put it in its own function. We'll say update window size, and we can move that into a function. So let's go ahead and define that. Update window size. There we go. Do this. Awesome. So now if we're here, we know our bar length should be equal to columns. It should actually be equal to columns minus something. So figure out how much buffer room is needed. Okay, so we have to figure this out. So we know that we have, like, let's say I equals 0. Then we have the 2 square brackets. So I plus equal 2. It's not a great way of doing this. We can put this all in one line. So we can do I equals 2 for the number of square brackets plus the length of the bar. This is just the buffer part of it, so we're not actually going to store that yet. So we have that plus 1 space plus 3 for the string of CPU, just the literal C, the literal P, the literal U. Now we need something for the number of CPUs. So we know it's 1 here, but we need to know the max length of all the CPUs. So we should actually go and calculate that out. We can do that here. We have the number of CPUs we have because we've already read the proc data. We have that in our variable called current. So if we get the length of current, then we're going to know the max size of the CPU. However, there's some weirdness with that. I haven't gotten to the weirdness yet. So instead, what we're going to do is we're going to loop over every single number in there. We're going to keep the max number. So the max number should technically be the last element of the array. If we have the last element of the array, we have the maximum number. We can count how many characters are in it. We can treat that number like a string. So instead, we'll do it this way. We will say highest CPU equals current at -1. We can index an array backwards. This will get us the highest possible number of CPU, and then we can get that as an actual length of the string. So instead of 1 here, we want the length of the string of highest CPU. That's going to get a little bit hard to read, so I think we can actually do this. We can do 2 plus 1 plus 3 plus, so we can do this. Square brackets plus space plus CPU. So we have to know the exact format string here to make this make sense. Length of CPU number. Okay. Now, what else do we have? When we run our script, we have the length of the CPU number, and then we have, oh, well, it's not so great that our script is actually currently broken. So that's not great. Let's think about that in a second, though. But we have our percentage. So our percentage is a number with a period and another number and a percent sign. Now, here's the thing. What's the biggest thing that could be? The biggest number could be 100, right? 100.0 percent sign. So whatever the length of that is. So 1, 2, 3, 4, 5, 6. So 6. So I'll put 6 here, and then we'll do pound sign that. So we know where that 6 comes from. Now that we have all of that, we can do columns minus I. There you go. So let's go ahead and do some work here. Let's make this local. Let's make this local. I have a feeling the syntax might just be wrong, and I'm wondering if this is why it's breaking. So we'll have to double check that. Let's do a bash minus X on this. All right, so it's not liking what's going on here. We wait for data. We sleep 1. And then we do all this stuff. We trap, we printf to go into the alternate buffer, hide the cursor, update the window size. I have a feeling it doesn't like that, but we're going to figure out exactly why it doesn't like it. Okay, so this was gnarly. It did not like this syntax, and the reason it wasn't showing up is because I was in the alternate screen, so this can get super annoying, like just super annoying. So to debug this, I'll show you guys what I did. Basically, where I did this, I just decided to comment this out. That way I wouldn't go into the alternate screen. I just had a hunch that this function was the one dying, obviously, because it was the one that we wrote and it's broken. So let's go ahead and run this. And you can see that we get these nice little messages here. So you can see at line 14, it just doesn't like this syntax of it. So this isn't going to quite work for us. It's a shame. I would like it to have worked. I don't know how else I could represent this data. So instead, we're just going to put a little note here for ourselves of like this plus that plus num plus 100.0%. So if we just do this, then it can be cleaner. We can just do 2 plus 4 plus the length as a string of the highest CPU plus 6. So if we just do this, this should work, and this should work exactly how we expect it to. So we're not quite going in the alternate screen, so it's going to be a little bit gnarly. We're messing up the screen, but hey, look at this. That at least gives us something. Okay, so still it's not really right though. Like, take a look at this. Like, am I crazy, or is there just a lot of space over here that seems like it's not being used? It seems like we should be going past that. So let's do some printf style debugging and see what's going on here. Echo highest CPU equals highest CPU. And then down here we can echo $I. I'm very curious what this one is set to. So let's have columns and then $I. So we'll do that. We'll run this and we'll see what we get. Doesn't help if we keep clearing the screen. So let's go ahead and get rid of this and get rid of this and then echo this without the minus n. So doing a lot of a lot of debugging on the fly, but hopefully you guys are enjoying this. And yeah, okay, interesting. So, oh, well, that gets cleared when I control C it. That's annoying. But look at this, 86 and 28, and the highest CPU is this. So, okay, I already see what's going wrong here. All right, this is crazy to see. It's the same mistake I keep making. It's so funny that I would keep making this mistake. The highest CPU, what are we doing here? We're getting the value of it again, which is a number space a number. We want the key. The terminal keeps getting messed up, but take a look at this. There we go. Highest CPU is this. That's not right. It's pulling out the value. I want the key of that. See what the problem is? See how annoying that is? So we're gonna have to do a little bit of work, unfortunately, to get that data. Because if you look here, we can see the highest CPU is equal to this. You can't just put an exclamation mark in front of this and extract the key from it because we're using this syntax to use the key. So instead, what we're gonna have to do, which is a little bit annoying, we're going to have to make a new array of all of the keys of the CPUs and then index into that array backwards to get the last one out of it. So I will show you what that looks like. So we have to do something silly like this, like CPUs equals make a new array and then loop over the keys of all the current array or CPUs that are there. So now we have a new array called CPUs, which has all the keys that we have, and then we can index into that one, assuming I don't delete it, index into that one backwards. So now we will have the highest CPU, and it should be like 3 or something. There we go. That looks right. So a little bit gnarly what's going on here. Let's get rid of some of these echoes. Let's go down here and bring back in some of this stuff. So yeah, that was a bit of a mess. I promise I prepare for these videos, but it is kind of fun. I had considered just completely cutting all of that out, but I do think it's fun to try and show like some of the actual debugging that goes on in here, and also show that some of you guys in the comments, hey, I'm human. I make mistakes, especially if you want to see me make mistakes, go watch my live stream. Oh my God, it's just nothing but mistakes. It's so funny. They're fun. They can be fun learning experiences. So hopefully that was useful for you guys. Also, if you made it this far in the video, you're like a super fan, so I appreciate it. Thank you for watching. Go ahead and hit the subscribe button. I'm not going to ask you to do anything else. Just hit that subscribe button. I like seeing that number get bigger. I want to hit 100,000 subscribers by the end of the year. So look at this. Look, it butts up right against the end. As you can see, there's some breathing room here. There's some breathing room because this percentage could technically be 2 characters bigger. So that's why that breathing room is there. So we have successfully created breathing room for this. Now, the beautiful thing is, say we were to make this terminal smaller and then we run it. Look, it's the right size. Isn't that amazing? Let's go ahead and make this terminal bigger. Uh-oh, didn't actually make it bigger. So what's going on here? What do we do about this? Well, we have to, when the terminal is resized, we have to react to it. We have to call this update window size thing again. Technically speaking, we could call this every iteration. We could just straight up call this function every iteration and we would be fine. Before we display the user information on the screen, we could call this and we would be fine. But instead, it might make sense to just call this when the terminal's size is changed. So we can do that with another trap. So for trap cleanup, we can change this to update window size, and we will change this to winch. Sig winch or window change will tell us when the window has changed. So if we put this here, this function will get called whenever the window size is changed. So if we go ahead and we run this now, it'll work. And let's go ahead and resize our terminal. Look at that. Look at that. I can make it gigantic. It's kind of cutting off the screen, but like you get the point. If you make it like this, look at that. Look at that. That's crazy to see. I don't know why you'd ever want that, but that's like really, really cool to see. So let's go over here, make it as big as it once was before, or at least get somewhat close to it. And let's make sure I didn't break anything. So if we do like a tmux new, and we run this, and then we open up another one down here, and we do a nice little while loop, we should be able to max out 1 core. So there you go. Look at that. Are we off by 1? Oh man, do we have an off by 1 error here? Oh, wow, that's so fun. Where are we missing? Ooh, we just got scheduled to a new core. How fun is that? That was fun to see live. Yeah, let's go ahead. Let's move this down a little bit. We probably move that down 1 more. There we go. Let's go back up here and let's do some editing of that. So what I mean, we could just add 1 to this. Obviously, we are just clearly off by 1. But where is that 1 coming from? We have 2, we have 4 for CPU, we have the actual number itself, which is the length of the number. Oh, there's a space here. There's a space between the CPU number and that. So that's all we were missing. It was just a simple off by 1. So now if we run this with that busy wait still running, we can see that, hey, look at this. That looks pretty good. Look how fancy this is. This is so much fun to see. This is so cool to see. And we also have the ability to give it, no color equals 1, technically equals anything. And now we have the no color variant of it. So this is really cool. We have done some really, really cool stuff with this. There's one more thing I want to show you in this video, okay? There's something really, really fun I discovered while working on this. And I'm not lying, this is like actually really fun because it's going to be kind of wild, okay? So here, let me kill this. And you can see that, okay, the machine's not doing anything. That's great. It's just kind of sitting there. Well, remember how I talked about we're using the Proc file system to read this information? There is also the sys file system, the SYS file system. Well, let's talk about some of the stuff that is in the sys file system. So if we do ls sys, there's devices, then system, then CPU. Take a look at this. There's a whole bunch of stuff here, but look at this. CPU 0, CPU 1, just completely refresh my terminal. Didn't like that. CPU 3, I'm gonna stop clicking my terminal. Apparently that causes problems. So each CPU has its own directory. Let's go ahead and look in, I don't know, CPU 3. Look at this. There's a file called online. It's interesting. So if we look at that file, let's go ahead and cat that file. Oh, well, I'm never gonna get used to using tmux, using control A. I mean, I should probably switch that to control B. I think I'd be a lot happier. Cat that, look at that. It has 1 in it because it is online. Could we make that offline? Well, let's go ahead and become root. So here we are. Now we're root. Let's go ahead and echo 0 into, what was it? Sys, devices, system, CPU, CPU 3, online. We're gonna go ahead and echo 0 into that. Uh-oh, look at that. It just got completely eliminated from our output here. We turned off that CPU. It is gone. Our system does not know about it anymore. If we look at, let's do head -5 of proc stat, you can see that, oh wow, that last line's a little bit long. Let me do head -4. It's just gone. CPU 3 is missing. We've offlined it. That might be a little bit confusing. Let me go ahead and turn it back on for you. So we echo 1 into that file. Look, instantly back on. We instantly get stats about it again. So our program's handling it fairly gracefully. For not considering this, our program's doing a very good job. Let's go ahead and turn off CPU 1. I think this will illustrate things better. So we turned it back on. That doesn't do anything. Let's go ahead and turn this off. There we go. So now that it's off, as you can see, it really doesn't like that. It really doesn't handle that well. It thinks all of the ones are off below it. That's not ideal because it's not actually what's happening here. If we look at proc stat, we have CPU 0, but then we have CPU 2, we have CPU 3. So like, what's going on here? That seems a little bit suspicious. In fact, let me show you something else. Let's take a look at htop. Look at how htop handles it. Offline. htop is very graceful about how it handles it. It's a very nice way of handling it. Wouldn't it be nice if our tool could do the same thing? Well, that's what we're going to do. So let's figure out how to do that now. Because ours seems to break when a CPU just becomes offline. If we run this, we can see that it shows, oh, CPU 0, CPU 2, and CPU 3. Great. Even more confusing now. Okay, so it's gone. What if we turn it back on? We have echo 0 there. So let's go ahead and echo 1 into that. If we turn it back on, hey, it shows up. That's great. What if we echo 0 there? Okay, now everything gets wiped out. Clearly not ideal, clearly not what we want. So let's go ahead and figure out a nice way of doing this, a nice way of bringing up all the CPUs. How do we do that? Well, procstat doesn't have the information we want because if a CPU is offline by the time we read procstat, it does not show up in there. It doesn't show like a blank line. It literally just does not show up in there. That's not good. But where it does show up is in sys. Okay, it's gonna be a super awkward cut. The power flickered here, and luckily I have everything on like a battery backup, but I don't remember exactly where I was in the recording of this video. So we're gonna just hope that I haven't talked about any of this stuff before, and I'll try to do my best when I cut it all together. So basically, we need to enumerate all of the CPUs. We have the sys file system, so we have sys devices system CPU. As you can see, we've used this below. We've turned on and off CPUs by using this online file here. Well, we have CPU 0, CPU 1, CPU 2, CPU 3, CPU frequency, CPU idle. It's not great that there's other things there, but here's what we can do to get around this. We can list, instead of CPU star, which will list everything, let's go ahead and echo that. Even that's a little bit confusing. Let's go ahead and use printf. Wow, I hate using tmux. I'll never get used to it. I just need Control A to be something else. Let's put a format specifier here, %s with a new line. Now you will see what they look like on separate lines. This is great. What we want here is we want a number. So it needs to start with a number and then has star, so anything to the right of it. Technically speaking, if Linux decides to add something like CPU 0 foo, this will break. But as of right now, they don't have that. So this seems to work just fine. We can use CPU 0 through 9 star, run that, and it works how we expect. We can get all of the CPUs enumerated this way, whether they're online or not. Because remember, one of the CPUs is actually offline right now. So we can grab this. We're gonna have to do some string manipulation to trim off some of this directory name stuff, but we'll worry about that when we get to it. We want this line. This is what we care about. So let's go into our script here. And where do we have? We have our read proc here. Before we even read proc, we should read all CPUs. So we're gonna gather all the CPUs before we even do anything else. So let's go ahead and implement this. Read all CPUs. And here are all CPUs, a new array of this like that. We could put that as local. So we have all CPUs as this. Now we have an array of every single CPU that we were able to find. We could declare -p all CPUs and then put an exit 1 here so we can just make sure it works. So if we run this, there we go. We've printed every CPU that we found. Now it's not great. We do have all this stuff that comes before it. We don't want that. So let's go ahead and trim that off. The beautiful thing about Bash is if you've ever used parameter expansion, you kind of get the same thing with arrays. So this is going to blow your mind if you've ever seen it. All CPUs equals a new array. We're going to create a brand new array here. And what goes inside it? Well, the same thing that's already inside it right now. So it's all CPUs with this notation to expand the array. If we leave this as is, we haven't made any changes. We've just copied the array over to a new array of the same name. Completely just worthless thing to do. What we want to do here is we want to, from the left-hand side, greedily match anything up to the last slash and remove it. It's the same as parameter expansion. Pound sign means delete from the left. Double pound sign means greedy about your match. Star means anything, and slash means a literal slash character. So we match everything up until the last slash character. So let's just go ahead and run this and see what we're left with. Hey, look at this. CPU 0, CPU 1, CPU 2, CPU 3. These are all the CPUs we have been able to find. That's really cool. Now, the last thing we want to do is, because it's an indexed array of all the CPUs, we even want to chop off this beginning part, this CPU, CPU, CPU. We can chop all that off just by using the same line here where we match the literal slash. Just put CPU here. There you go. Now we're going to strip off the CPU. It is so windy out. I hope the power doesn't flicker again. So look at this. So we have 0, 1, 2, 3. So these are the CPUs that we were able to find. As you can see, they match up to their indices here. I don't know if they necessarily have to, but either way, the values of this array are the CPUs that we were able to find. So instead of using local variables here, we could just change this. We could say all CPUs equals this, and then all CPUs equals this, all CPUs equals that. So we'll make a global variable of all CPUs. There you go. We can get rid of this declare. It doesn't technically need to be there, because when you use declare, it just creates a regular array, as long as you use the open and close parentheses. If we do that, I wonder, should we just change current to be all uppercase current just to match the style? Probably, right? Let's just change this to be all uppercase current. Let's change this to be all that. So now we can just do a nice little search for current. We can just change that, change that, change that, change that, change that. There we go. Just go through each one and change them. Then we have what? Previous. So we could change that to previous. There you go. There you go. So again, we haven't changed anything. So we should probably make sure that this still works how we expect it to. And hey, that looks pretty good. All right, so things are kind of working how we expect them to. So what do we do here? Now that we have all CPUs, we have an array of all CPUs. This is super useful, because when it comes time to read the proc data, we can initialize the current data here, okay? So what I mean by that is, before we just start reading data into current, we can do some work here. Say current equals an empty array. We're going to completely overwrite it. We're going to set it equal to 0. We're going to clear it out. Now we could do for key in, we've already declared key as local, which is very nice, in all CPUs. There we go. We have this all CPUs array. So now we can just initialize current key equals anything. It doesn't have to be set to anything, but we can just set it to anything. That way it just shows up. We at least have it there. We know that there is something there. The issue, of course, let's get there, is that when we go to enumerate it, we're going to see that there's like something there, but it doesn't quite work as we want it to work. What I mean by that is, it's an empty string. We never overwrite it. So when we get down to our print bar function, some of these are just going to be empty. Like, that's not ideal. That's not what we want. We could break out of it. We could say if -z busy 1, doesn't matter which one, -z means is not set, then we could just return from this. So if there was nothing set, then we know that it's been an offline CPU. So we can go down here and we at least get the other CPUs there, because we've broken out of the print bar function early, because we know that it's offline. So we could do a check like that. That's totally fine. That works. We could also be a little bit more forward thinking with this. We could be a little bit more clever with this, okay? So if we get down here and we know that this one's empty, or this one's empty, or this one's empty, and we could check all of them. It doesn't seem necessary, but we can just check these two. If we know that either last iteration or this iteration, it's offline, technically it could come back online, but we're going to need 2 iterations before we can actually get some meaningful data. If either one of these is true, then we know that the CPU was offline at some point. So check for offline CPU. So we want to make some changes based on this. So look at this. We do all this math down here, and this math kind of relies on things not being 0, because we don't want to divide by 0. So things get a little bit gnarly here. So let's do this. Offline CPU, else online CPU. So let's get rid of this return. And what should we do in the event of an offline CPU? Just say that the usage is 0. Now, if it's online, we do have to do a lot more work here. So let's go ahead and put this here. Let's bring this up a little bit, and let's declare the usage here, so we can get rid of this local keyword. We're going to want this out of the if else branch. And then let's just make sure we're using all the right variables here. So we have the usage thing being used here, the usage being used here, blah, blah, blah. This looks pretty good. If this works how we expect it to, when the CPU is offline, it should just get a straight up 0. So it should still show up. It still shows up, but CPU 1 will never be anything other than 0. Almost there. We are almost there. That's great, but we might want something else. We probably want some sort of notification that lets us know that it is offline. So where do we put that? Let's set a Boolean flag that we can use. We can say online. Now we have online here. So we could say if it's here and it's offline, then we just do online equals nothing. Otherwise, we will say online equals 1. So we can check if this variable is set, and that will let us know if the CPU is online or not. So here we go. We have this bar graph, which will be empty. We have the CPU name here, and then this percentage thing, right? We have this whole percentage thing. Here's what we can do. We can say if -n online, so we know the thing is online, then status or stats or state, we'll just use a new variable called state. If it's online, then state is equal to the percentage with a percent sign, okay? Otherwise, if it's offline, then state equals offline. There we go. So now we can close that. We can go back here, and where we have $perk in here, get rid of that percent sign, get rid of $perk, and just put state. There we go. So let's run this and let's see what happens. Well, we kind of flow off the screen, but this is actually really nice. We don't have to calculate the max percentage. We just have to calculate the length of this longest string, offline, OFFLINE. What is that, 7 characters? So let's go back to where our percentage calculation is. Where do we do that? It's in the update window size thing here. So we +7 for online, but now there's a space with it. So offline, this will technically be 8. So we change that to 8. Go ahead and rerun this and look at this. Now we have a way of noting if it's offline. So that is pretty cool. We could also change the color a little bit. So we can move the color out of, I'll just show you what I mean. Okay, so we have the color is set to color 3 down here always. We can just get rid of that. We can get rid of that, get rid of that, and now we can do this. So we could just do state is color 3, percentage, reset. And then for offline here, we can just say state is dim, and then offline, and then reset. So we can do something like that. I don't know how this is gonna look, but let's go ahead and run this. So now the word offline should show up as gray. Hey, that is really, really cool. Why is this one showing up as dim? That's kind of, okay, I kind of like that. It doesn't mean anything, but it's kind of nice the whole line is dimmed out. Oh man, I actually kind of like that. That's because I put rest instead of RST. I love bugs that show up visually that are so much fun to see. Let's go ahead and change that back to RST, but we should consider maybe dimming the whole line. That is kind of nice. Look at this. That's awesome. Now we can see that it is offline. If we go down here and throw ourselves into a busy wait loop, we can see that. Look at that. We've pegged one of the CPUs. So now that we're down here, we can do, what do we, echo 0 into CPU 1. Let's go ahead and turn off CPU 2. There we go. Look, the CPU just went offline. How cool is that? Let's turn off CPU 3. Look at that. The CPU has gone offline. Of course, guys, if you're watching this video, of course we're going to try it. Don't worry. Of course we're going to try it. You already know where my brain's headed. Let's turn off CPU 0. This is a virtual machine. Shouldn't cause a problem, right? Linux won't let you shoot yourself in the foot. Linux won't let us do that. What's actually happening here is this file doesn't exist. We're root, we should be able to write here. So this permission denied actually means that we're trying to create a file there. If we go and we cat this, you can see that it's just not there. We can't turn off our main CPU. Linux needs at least one CPU to run on. Someone in my live chat before when I was working on this said that you might be able to custom compile Linux with the ability to do this. So that could be wild. But for now, we can't do that. But let's go ahead and turn some of those CPUs back on. So we can turn CPU 0 back on. Nope, CPU 0 doesn't exist, right? Let's turn CPU 1 back online. And it should show up after a second. There it is, nice. So it does take a second for the new stats to get brought in. So look at that. Now all of our stuff is back. If we rerun that while loop, we can peg 1 core. And there we go. We have CPU usage with colors and the ability to grow and shrink. The terminal should dynamically handle it. Look at that. Sig winch handling it like a champ. It's incredible. It's incredible stuff here. So yeah, I don't know what other function or what other features we would need for this. Maybe taking some options to allow the user to customize the bar character, but this is all pretty straightforward. I feel like this is stuff that, you know, if you wanted to implement on your own, you can go ahead and do. The only other thing I think I'd point out here is, what do? We call sleep. Sleep is technically an external tool. Now, remember I told you guys we're going to use all bash built-ins. Technically, sleep is external. It's a POSIX utility. It's going to be there. Your version of bash might have a built-in sleep. So it's not built in here, but if I were to log into like, here we go, now I'm logged into my Mac, I can enable sleep. It is a bash built in, so I can use it. On this Linux system, I don't have it. It's not the end of the world, so I'm gonna say external utilities plus sleep. There are some hacks to sleep in bash using the read command, but we don't need it. We're just gonna use the sleep binary. So we're just gonna run sleep every second. Not a big deal. But yeah, take a look at this. This is pretty cool. I think we've covered most of our bases here. So we have a nice little tool that runs and gives us CPU usage and utilization. And this is awesome, just using the Linux proc file system with bash. So this video ended up being a lot longer than I thought it would be. Okay, I truly thought this would be one of those videos that I would get done in like 30 minutes and we'd be good to go. This is so much more advanced than I thought it would be. So because of that, I wanted to cover network usage, network interface usages. I wanted to cover disk utilization. I wanted to cover RAM usage. I wanted to cover all sorts of stuff. There's gonna have to be a part 2 to this video. I'm sorry, I normally don't like to tease stuff like that, but we're gonna have to have a part 2 where we cover some of that stuff and kind of build out a whole dashboard. But I figure this CPU usage thing, this is a good jump off point. This is a good stopping point. So yeah, thank you for everyone for tuning in. I appreciate it. I'm glad you guys are watching and enjoying the content. I'll have all this code online. If you're not subscribed to the channel, what are you doing? Go ahead and hit that subscribe button, okay? I just turned on channel membership, so if you want like custom emojis and stuff in your comments and stuff, go check that out. I also have a Patreon, go check that out. And yeah, I'm gonna be live streaming more often. No set schedule, but I'll just be on when I'm on. So if you see me live streaming, come jump in the chat, say hi. So yeah, hopefully you guys enjoy this. I had a ton of fun writing this. I don't think we have anything else to cover. I think that's basically it. So thank you all for tuning in. And of course, I want to give a shout out to my patrons over at Patreon. Thank you so much for supporting me on Patreon. That is so cool. Take a look at this. This is insane. 82 active members. These are people paying me real money. You guys are super awesome. I appreciate it. Yeah, I just never thought making content about bash scripting would actually, entertain people, that people would want to learn about it. So I appreciate it so much. Obviously, hit that subscribe button. I got the bash course up. Go check that out. It's a free video. It's on my YouTube if you want to learn bash. Yeah, I think that's it from me. Thank you so much. Thank you for hanging out. I need to go get something from my throat because it's killing me because I'm getting over being sick or just starting to get sick. I don't know. Who knows? So yeah, thank you everyone. And that's it. See you guys. Take care.